All right, let's start. Do you have any questions? Okay. So last time, right? So let's pick up where we started, where we left off. So we were talking about exotic options, right? And we were discussing the PD, right, for exotic options. So let's kind of remind you, right, on the overall kind of point of view, right, on the PD itself, right? So how do I say this, right? So you kind of understand what PD is about, right? We didn't do this so much because we were looking at from the Greeks' point of view, right? So now let's kind of look at a little bit more like holistically. So basically, right, so what do I have in mind when I say this, right? There is another point of view, which is I would say the stochastic point of view, all right? And it's kind of important that you distinguish these two and you see how they're connected. So let's take the stochastic point of view first, right, for you to see. So the stochastic point of view is this, that again, right, our time interval, right, is from 0 to big T, right? And at 0, right, things are deterministic, right, known, everything like that. But any time after, right, 0, then, right, all the value will be stochastic or random, because basically, right, this is where we are right now, right? Everything to the past has been seen, has been known up to the present, right? But anything in the future, right, including up to the terminal time, right, will be unknown, right? It's random, right? We don't know what it is yet. Well, so how this applies, right, to the option pricing problem is that then, right, we have a underlying process called, right, the price process. I mean, usually we think of this as stock price, but it could be commodity price, it could be exchange value price, right? Things like that. Well, of course, you have to be careful to model this to reflect whatever asset you're modeling. But the point is, right, we will have a underlying process that we model, right? Where, again, right, S0 is known. And beyond that, right, ST is stochastic, right? Or T positive, right? And of course, ST is this is, even though it's stochastic, right, the model of ST is given, right? Think back Black-Scholes. Now, then, right, on top of this now, right, we have our option, our derivative, right? Which, of course, right, follows exactly the same principle that, at 0, V0 is deterministic, right? But here the story is kind of reversed in the sense that, so, again, right, let's just write down V0 is deterministic, Vt is stochastic, right, etc. But the story here is slightly different in the sense that, right, at no point, right, on the other hand, right, Vt for t less than t is not directly given, right? So that's the kind of opposite point of view compared to the stock, right? The stock is completely given by the model, right? At any point, that's the modeling side. For the option, on the other hand, right, except at the expiration time, right, where the payoff is supposed to be done, right? Otherwise, it's not directly given, right? That's the whole point of pricing, right? We have to figure out how this relationship is. So in other words, right, you have V big T, right, is given as a function, and you could, write it very generically like this, right? So it depends on the whole path. And of course, this actually covers the European option as well, right? Because depending on the whole path, you can just collapse it to only one point at the end, which, right, is a European option. This way of writing does not cover the American option, but we'll worry about that later. The point being, though, that I want to emphasize is, right, for option, right, only the value at time, the terminal time is directly given, okay, right, stochastically still. But the point is now we want to figure out, right, V little t, right? And so that's exactly pricing, right? Now, but now if you look at this further, right, the stochastic point of view actually is a bit kind of irresponsible in a way. It just says this, well, easy, right? I'll tell you this. Okay, that's it. So this is the stochastic point of view, meaning that, right, tell me what information is available up to time little t, or in other words, right, what kind of information is. So it's implicitly understood that this is the information generated by, right, the stock. Yes, if you give me all the information up to that time little t, I take a conditional expectation of the discounted, right, payoff function, then I should get whatever, right, that option price at that time little t is, right? So notice it's still stochastic, right? Supposedly is given by this formulation, but beyond that, right, you don't know much. So you can do, Monte Carlo simulation, right? You can do some probabilistic calculation, right, etc. So notice that actually this is how we derive Black-Scholes, right? We derive Black-Scholes formula exactly by probabilistic calculation. All right. But you have to kind of observe that in general, right, this way of doing things don't give you more than that. But actually, okay, now go back to the PD point of view, right? The PD point of view actually, maybe another way to put it is more like the Markov, right, property point of view, like this, right? It would say that, right, well, we can say more than this, all right? We can say more than this. And actually, in some way, when we do probability calculation, we use the Markov property already in this way that, so when you write big V like this, right, you just mean a random variable. You don't necessarily say anything more than that. But in the Markov property, you go a step further and you say, well, this random variable actually has a further structure, right? It should be a function of time and the stock price and possibly something else. All right. The emphasis, though, right, is that this is a known deterministic function. In other words, right, so the word known is a little bit vague. Actually, a lot of times you just cannot write down. So maybe I wouldn't write no, right? But basically, in principle, you could know it if somehow your math is really, really good, right? So let me just say that it's a deterministic function, okay? But I want you to appreciate this point of view, right? It's a little bit hard to see, but like this is only a random variable, right? You have nothing more to say about this. But here, basically it says that, right, you have a function depending only on time, stock price, and of course, right, if it's European option, then that's it. That's all you have, right? And so it's really nice because it further elaborates, right, how the option price is linked, okay, to these underlying processes, right? And that's actually the point of pricing. Pricing should not be just about statically given a number. Pricing should be about pointing out the relationship, okay, between this option price and the other, right, underlying processes. And so a lot of times you would see from the PD point of view, right? Now we can look at the point of view of PD, because one thing you should notice is PD is all about deterministic values. So there's nothing random when you talk about PD. All right. Which might seem a little bit strange because, right, we are dealing with stochastic process, right? And so the way you think about it is like this, right? So you have VTX, all right? So that's, let's say, the Black-Scholes PD. Okay. And so VTX is meant to do what? VTX is meant to tell you, right? So the way you think of it like this is like this, right? So here's time, right? Here's space. Here's big T, all right? And so again, we haven't talked about this so much either, but when you look at a PD, one of the very important thing you want to look at is the domain of the PD, all right? What values of T and X are legal, or what values of T and X are the ones that you want to consider, right, for this PD. For example, right, it's obvious that we do not look at time beyond expiration because there's nothing to look at there, right? Also, so by Black-Scholes PD, right, I mean, let's just think of call option, right? With expiration, big T. Now, we obviously also do not look at negative stock price because that makes no sense either, right? We don't look at negative time because that means in the past, right? Option has not been written yet or something like that. We don't care, right? Or more like everything in the past is known, so we don't care, right? So for the Black-Scholes PDE, the domain of interest is like that, right? Everything like this, all the way up. Okay. Why all the way up? Because there's no upper limit on how high the stock price can go, right? Of course, we implicitly understood that the higher region has a very small probability, right, of reaching there, but the PD doesn't care about that. It's just about this whole region are the legal values they consider. So let's say, right, you have a PD written out, meaning a complex relation between the partial derivatives and the value of this function, right? So again, you just look from the PD point of view, you simply look at this as some function of T and X, right? You don't know what it is, but you do know that it satisfies the following relation, Vt, right? V sub x, r times x, plus 1/2 Vxx, sigma square, x square, minus r times V is equal to 0. Furthermore, right, you know that this is true if we're looking at a call option, right? If we look at put option, whatever, we change that, right? We changed this so-called boundary condition. So, right, what happens? What happens is right here on this strip, right, on this line right here, this is exactly VTX. You know completely, right, what the PD value is or what the function value is. Okay, and then normally, right, the way you do numerical solution is you start from here and you back solve, right? You back solve. You go back, right? Using this relation, you discretize in time, you go back, right? If you pay attention, that's the whole, again, right? The whole study, okay, on numerical PDE, you have to understand what the numerical algorithm is doing, but most of the time, or I would say all the time, it starts from the known values and it try to propagate back, right, approximately to the past, okay, or to the regions that you don't know the value. So, but right, to comment, so you would ask, right? So, okay, let's say you're a quant, right? And you are a PD quant, meaning you don't know anything about stochastic, you just do your numerical stuff. Then the trader comes in, right? The trader would be like, well, okay, you got a nice PDE, but now, right, I want to know what ET is, okay? How do you tell me that, right? Because that's what I pay you for. I didn't pay you to solve the PDE. Exactly, I pay you to tell me this. And you're like, okay, right? Well, we know what T is, right? Because that's exactly what V little t is. Well, but also at this time, it's implicitly given that ST must also be given. Because at that time, you must know what the stock price is. Okay. Then now you have this PD solved. And all you have to do is, again, right, re-invoke this relation and say, well, just tell me what this guy is. And I will just plug into my equation solver and output this value for you. Okay. In other words, what's happening is, right, when you have the PD solved on that this time little t, you know the value of V on any time on this strip, any values on this strip, right? What the trader wants is a particular point on this strip. And you just ask him what point you want, you plug in and you tell him what it is. Okay, so that's what the PD is doing. That connects it back to the value of the option. Any question about this? Okay. So now, right, so that's just our overall point of view on the PD, right? Now, for the exotic options itself, right, what do we want to say? For exotic option PDE, and it would be good for you to, right, compare it with the Black-Scholes PD, right, in the past, right, in general, because you want to see what's the difference, all right, to appreciate what the PD is doing there. So you will see later on, right, that for exotic option, so for Black-Scholes PD, I mean, I guess technically they're all Black-Scholes PD, right? Maybe I should call it European PD or something. So for the European PDE, right, the value of the option will be only a function of time and the stock price. Okay, and this comes from the Markov property of the stock, but also, right, intuitively about the option being not path dependent, right? So the logic is like this, right? You say, from the point of view, right, of risk neutral pricing, let's just take call option, right? So this is the overall pricing equation. You want to know the option price, right, at time t with, right, a future payoff like this. Now, this means that you have the whole past, right, of the option of the stock price up to time t available to you, okay, like this. So it's like you kind of observe this path, right? This is stock. All right. Now here is the future, and exactly right where it goes is unknown, right? All the possibility, right? You know that here you get paid as big T minus K plus, but you don't know what path it will take, right? Of course, these are all right. You could simulate this out. But the point is though, right? Because the way the stock is constructed or the way we assume how it works, you to simulate all this path because, right, you know, the payout in the future only depends on the value of the stock here. And the value of the stock here only depends on where it starts. And it doesn't really depend on the whole history. Okay. So therefore, right, even though you observe this whole path, you know, that's what's given to you. All you really use is the stock price at time little t, right? The stock price at time little t, which exactly collapse, right? The dependence here on the T and ST. All right. So that's why the PD for European option, right, is only a function of T and ST and nothing else. The story, right, should change when you look at exotic option. So like I said last time, right, with exotic option, it should depend on time for sure. It should depend on the stock price for sure. But generally, it should depend on something extra. All right. But this dependence, right, by the way the dependence is written out needs to be carefully studied, right? You have to understand how the process works to know what this extra thing is. Okay. But the general idea is you cannot just have a dependence simply on time and stock price, right? For example, let's take the, you know, well, look back option, right? Again, the beauty of the, you know, risk neutral pricing formula is that doesn't matter what payout structure you have unless it's American, you can just still use almost the same pricing equation, right? However, what changes what comes out here, right? What comes out here if you really want to write down the relationship. But right, let's take a look here, right? Again, right, let's take this picture. So at time little t, right, you observe this path. You know that in the future, right, you will get payout this much at time big T. But now you see that this payout depends on the whole path, right? So of course, right, the future fluctuations out here, you don't know. But clearly, right, the max is taken over the whole path from time 0 up. So therefore, right, it cannot collapse to only this. Yes. Now, clearly, right, this part is needed because the future values, right, only depends on the current value, right? That's how the stock price evolves. So the new path only depends on this. So that's where this is coming in. On the other hand, right, because the option payout demands that it pays the whole max of the path. So this is wrong, right? It should be VTST, the max from 0 to little t. All right. So this is the running max, right? This is running max process that we talked about. Okay. So that's the difference in general, right, of exotic option and European option, right? For an exotic option, you can collapse, I mean, for option pricing in general, right? You can and you want to collapse the option price into a deterministic relation between time, stock, and whatever else, right? If the option is European, this is it. If the option is exotic, path dependent, then you need to include the past information up to that time in some way, right? Depends on how the option is structured. For example, with the look back, then you need to include the running max. So intuitively, right, with the Asian option, because it takes the average of the whole path, then at time little t, you need to include the integral, right, up to time little t. Okay. Any questions so far? Okay, so yes, right. So actually, that question is right. Why PDE in general, and that's actually something, right? Yep, I did mention, but I also want to repeat. So why the word why, right, is a loaded word. Depends on what you are looking for. So the first thing is, right, like I said, PDE gives a connection, right, between the Greeks. So financially, the PDE makes sense, right? Or financially, the PDE tells you some very interesting relation, right, between the Greeks. By the way, right, the talk of Alvin Huang yesterday, and when Stephen was talking about the gamma being bigger than theta, whatever, right? I think you can try to look at that from the Black-Scholes PDE point of view, and it should have some interesting information that comes out of that. Anyway, you see that, right? When it comes to exotic option, suddenly this PDE also involves some information about some extra process that you don't really, right? You may not be aware of beforehand, right? This is not one of those classical Greeks, right? This is going to be some interaction between the option value and the running max. But anyway, right? So financially, it tells you something that is interesting that you may want to watch out for in terms of finance. Now, in terms of practicality, right? Meaning, well, at the end of the day, you might want to know what numerically what this guy is. Then, right, you guys should have seen that you have only three options: analytical formula, Monte Carlo simulation, and numerical PE. Right? These are really three options that you have, and that's it. Okay. Now, when it comes to analytical formula, you should intuitively feel that, right? Working out this formulation is challenging and maybe impossible, right? I always kind of hesitate to use the word impossible with the students, because when the students see something that's hard, they might think it's impossible. So when you want to say something is impossible, you want to have a more careful reason why it's not possible, all right? It's not just because it's hard. It's because we really cannot do anything about it. Monte Carlo simulation, right? You guys should have a taste of it already, right? Very slow, if not if you don't plan for it. And in fact, right, your computer right now, which by the way, you should recognize it's a very powerful computer already compared to 20 years ago. And it still cannot handle a very reasonable, right, tolerance requirement. So that kind of says that, right? So here, I'm not claiming that numerical PD is superior to these two guys in any way. So if there's any message that comes out of this, it's like for a hard problem, you have to invest more thinking to get any reasonable result out of it. That's all there is, right? So numerical PD will give a good result if you know a good algorithm and you can execute it well. So in other words, right, the PDE from a computational point of view just gives you yet another approach. Right, to finding out the value of the option. Okay. So for Black-Scholes, yes, for Black-Scholes, this is the easiest. And then we don't bother, right, looking at the PD. Then the PD is just more like an exploration tool for us to re-verify our analytical formula. Okay. And also, Monte Carlo there is not too bad. So in fact, Black-Scholes is just a playing ground, right? By Black-Scholes, we mean the co-option. But when things start to get complicated, that's when you need to start looking for different options. Okay. And the more options you have, right, the more approach you have, the better you can have hope for, right, attacking the problem at different angles. Okay. And that's exactly the point of view of this, right? Even nowadays, with computer power as strong as it is, I would argue that this approach is not that much easier than this, because you need to learn more advanced techniques, right? And I guess the amount of time you spend learning that is probably the similar amount of time you spend learning numerical PD. It's probably preference, right? There's no clear winner between these two. And this guy, again, right, is just beautiful when you have it. Most of the time, you don't expect to have it. All right. Any other question? Sure. All right. So now, let us right now go back to the PD form of an alcohol, right? So what I want you to appreciate is the relational dependence between option values and the underlying process, why that is the case, right? Second, when we do the PD, I want you to appreciate what the PD is trying to tell you, right? From the Greek's point of view and from the computational point of view, all right? Learning how to solve it, right, is a part of a different class, right? I'm not responsible for teaching you that. Frankly speaking, I'm not an expert in, numerical either, so I probably can't tell you much. On the other hand, right, understanding what this is all about is the starting point, right? It does you no good to start solving the PD without knowing what the PD is trying to tell you. So for the up and out call, right? Notice that, right, first of all, we have the following observation. That VT, okay, so first of all, right, remember, we have this. So maybe let us backtrack, right, and tell you what it is. So V big T, right, is ST minus K. And like this, right, tau equal to T, right? Where tau is the first time that the stock price crosses the level L. Right? So here, right, this stopping time plays an important role, right, in the up and out call. So here it reads, right, if the first time that the stock price cross level L is after expiration, then you just get the payoff like a call option. If the opposite happened, right, if the first time it crosses the level, the barrier, right, is before expiration, then you get nothing, right? Then the option is striked out, right? The option is striked out. So that's L, right? T, right? So there could be two paths, right? This path, right, is out, right, for the stock. And this path, right, is in, right? Okay. Okay. And by the way, right, so for here is exactly tau, right, for this path. So we say, right, we observed that V little t for up and out call. Surprisingly, right, and this is where I want you to pay attention. is a function of t and st almost, okay? The path-dependent nature is right here. When the option has not been striked out, then, right, so as long as the option has not been striked out yet, then the value at this time can be described as only a function of t and st. So this should be a little bit surprising, right, in view of what I was saying about that extra dependence, right? So generally, it must depend on an extra thing, right? Not just on time and stock price. Here, that extra process is exactly this information right here. Okay. So in other words, right, you must always check, have you been striked out or not, right? But the intuition is clear like this, right? The intuition is clear like this. Well, suppose at this point, right? At this point, you have not been striked out yet, right? At this point, you have not been striked out yet. Then if you, from that point of view, if you looked at the option value, then what do you know, right? You know that you need to look at the future paths, right? Whatever that future path is, you don't know. But that future path, right, only depends on the current stock price, right? Starting at this time, generate the future paths, first of all, right? Second of all, because the payout structure only depends on the terminal stock price and doesn't depend on the whole path. Therefore, right, all you need is the current stock price to generate future information, as long as you have not been out yet. So you need to keep track of the past, right? But as long as you have not been out yet, then all you need, right, for future option value generation is that current stock price. Okay, and that's the rather deep point, right? Try to think about it and try to contemplate on it, right? Including this stopping time, right? Including this stopping time, because you have not been striked out yet, right? So from up to the past, you're okay. Okay. But to generate the future, right, including the possibility of crossing the barrier for the first time, that actually only depends on the current information, stock price. Plus, of course, the information that you have not been striked out yet, but nothing beyond that, right? You don't need the whole history of the stock to generate future path for this kind of payout. Okay. So that's very important. Okay, that's very, very important. Then the next thing, right, is about the whole idea that the discounted, right, stock price, discounted value process is a martingale, right, in general. So here, given this kind of information, right, the discounted stock price, the discounted option price is a martingale in general, but for a up and out call, is a martingale up to, right, the first time that the stock price crosses the barrier. Okay. And again, I told you that, right? Basically, this may be a little bit hard to perceive from the math point of view, but from the financial point of view, actually, is quite intuitive. This statement actually is just a fancy statement to say that, right? The current fair price of a future, right? The current fair price of, right, a share of the asset in the future is current price. All right. So that sounds like a little bit weird, but by the current fair price, we mean the pricing action. And the current price here is like the price in the market or something, right? So, again, right, what that means is E tilde, right? E to minus R, T minus T, V big T is equal to V little t, right? So this is the current fair price. This is the current price, right? And that exactly tells you this. Now here though, right, in the up and out call, right? The same logic as we said before. As long as you have not crossed the barrier yet, right? As long as you have not crossed the barrier yet, then when you look at this option, right? You ask, okay, what's its price? It has not been striked out yet. So if you're given a value of the option in the future, right? Whatever that is, then as long as, again, right, that value in the future has not been striked out yet either, right? Then of course, its fair price is going to be the current price, right? Notice, right? As long as that value in the future has not been striked out yet, then, right, its fair price is the current price. But of course, if the future has been striked out, then that value is 0. So it cannot be the current price, right? So that's why it's a martingale only up to that first time that's struck out. Okay. So again, kind of some easy intuition, but it relies a lot on you contemplating, right, what this option is doing and, translating that to mathematical language. But anyway, right? So this, all right, this statement together, right, with the idea that if something is a martingale, right, then D of that guy, right, which is something dt plus something, right, dw tilde t, okay, then this part must be equal to 0 because this is a martingale, so it cannot have any drift, right? This is already a martingale. The stochastic integral against a Brownian motion is a martingale. This is a martingale, so it cannot have any drift that changes it from its martingale nature. All right. Now, you see, right, combining that with the fact that, right, as long as you have not crossed the barrier yet, then this is a simple function of time and stock price. So therefore, right, your good old Ito's formula tells you, right, that this is going to be V sub t, right, plus V sub x r st plus V sub xx r st, sorry, sigma square 1/2, right? Minus RV, right? Like this. And then actually you still have the exponential outside. dt, all right? And you would have like that, okay? The point being though, right, is that because exactly the structure of the option is the same as the structure of the call option, right? It's almost a call option, you see. It's almost a call option, except for this information on the time that is struck out. So therefore, it's not too surprising, right, that in the main effect, the PD for the barrier option is similar to the Black-Scholes PD. Right? But I said that if you just remember this, then that's nonsense, right? Because this is exactly the same as the Black-Scholes PD, where we're there, right? Right? It's exactly the same. Even this condition is the same. right? Even this condition is the same. However, right, what distinguishes it, right? Because I mean, if you are at the terminal time, then you get paid this much. However, right, what distinguishes it is exactly this piece of information. In other words, you are limited to only between 0 to the barrier. And that, right, changed the domain of the PD. Plus, right, at the barrier, you are struck out. Okay. So only these two things, believe it or not, changed the whole picture, right? So in other words, the picture for the up and out call, right, will be right, and the domain, unlike the Black-Scholes, is only this much. Okay, where now you have two boundary conditions. You have this boundary condition where this is x minus k plus, right? Notice this is perfectly legal because what it means here, right? So remember, so now, right, you have to remember what I was saying about the meaning, right, of the PD, right, for this option pricing, right? So when we say, right, this is x minus k plus, what we mean is if you are at this time, right, if you are at this time, and you look at V big T, right, then you plug in. We'll talk about this a little bit. Here, right, it will be 0, right? And beyond that, right, you don't care because these are irrelevant values, right? Because if you are above here, then that means you always strike out. So automatically you're 0. So we don't care about this, right? And then, right, if you do numerical PD, you will start with these two strips and you back solve, right? You back solve to get all the other information in the interior domain. All right, any question on this? Okay, so yet again, right? I would say that if this is the first time you see this, there are a lot of information to digest, right? So what I want you to, right, and what I recommend you to do is to not pay attention. Yeah. I guess it's just, sure, maybe this. I guess X and S play the same role, so it's what we mean is exactly the same. Sometimes we use S for stock price, sometimes we use X for a spatial variable, but like the meaning we assign to it is similar, right? So yeah. Yeah. So what I want you to do, right, is to understand what the PD is trying to tell you, right, and the picture and why the picture makes sense. The other information, right, the technicality, you can try to digest later. Okay, so you're asking something like that, right? That's exactly you're thinking about it. But let me tell you this, right? Does it make sense for you to put a condition like that here on the PD? You're thinking in the right direction. Yes, I'm going to talk about that. Exactly, I will talk about that. But just purely from the PE point of view, though, does it make sense for you to put that information there? Right, no, because you don't even know what tau is, right? How do you put it there? Tau is something you observed in a different context, right? And that's exactly the peculiarity of the PD. PD is a deterministic object. it has no stochastic information embedded in it. So it's like I said, right? Again, I know it's a talk that maybe you feel natural, but the whole connection between this and this is a bit deep, all right? It's a bit deep. It's connecting deterministic object with stochastic object, all right? It's not that simple. So sometimes if you miss out on something, you might feel, yeah. So Fatima brought up a very good point. But I want to say this, right? I will address this, but I want to say that just from a PT point of view, there's no room for this because tau is a stochastic, right? A random variable. You can't put it there. There's no tau show up here. Okay. So I will talk about that. But first, right, let me talk about in this one is purely technical. So I don't know. I think you guys did not take numerical PD so much, at least for numerical analysis one. So did anyone do some numerical PD before? Somewhere, maybe in Casper's class?
Well, we did it in numerical a little bit.
Okay.
Like we solved the Black-Scholes equation by discretizing the time and stock price.
That's great.
Yeah,
that's very nice. But do you have any experience about working with boundary conditions? Or do you remember anything about that? Right. So the whole idea of PD, I'm not sure if you guys get that much, is you start from the boundary conditions, right? You start from the given information and propagate back. Right. Now, when you solve PD, right? And again, this is about experience. You got to pay attention to regularity because sometimes irregularity can really hurt the algorithm. Within this context, do you see any irregularity that's kind of staring at you? This may be an interview question, by the way, if you claim you know some numerical algorithm.
Maybe at like the corner at time capital T and L. Like
absolutely right. What's the problem here?
To the left, it's equal to 0, and to the right, it has like a positive value.
Right. I mean, not to the right. I know exactly.
Or it's like to the bottom.
Yep. Exactly. So Kareem exactly pointed out exactly the problematic issue in this PD, right? I mean, it's set up correctly, right? That's what it is. But if you were following the condition over here, then this point should have value 0, right? But if you follow the condition over here, then you would have value L minus K, right? Which is supposed to be positive because remember, right? K must be less than L for it to be financially make sense. So in other words, right? This is discontinuous, right? But remember, right? PD is supposedly a very smooth object, right? So that means that you have a highly volatile, right, action around this corner, right? So all right, whatever. Okay. And so that says several things, right? What does that imply in terms of the numerical algorithm, if you know it? So if you pay attention to this corner point, right, then what should you do? In terms of numerical algorithm. right? So I can only tell you this much, but this will be encoded in something called adaptive, right, algorithm, meaning that when you discretize, right, you don't just discretize everything equally in terms of size. You basically you step very carefully, very sensitively, right, around this point, very small. Because why? The rate of change is huge here. So a small step can net you a very big change. So you want to be very gentle around here, right? And then you can step further. You can step, faster, right, around here. Again, Cesar might be a better person to tell you more about this stuff. So that's one thing, right? You gotta pay attention to here, right? You cannot, with this PDE, use a regular discretization scheme. All right, doesn't matter what you use. You must be more gentle around here, right? And you can do whatever you want around here. I mean, not whatever you want, but you can be a little bit more generous around here, right? Now, second of all, right? Financially, does this make sense? Financially, what does it tell us around here? Does it make sense? Financially, that what's going on here? Why is this problematic? So yeah, right now that you see the math, you have to connect back to the finance, right? Does it make sense that somehow your object is behaving weirdly right around here? Sometimes that's just a sign that your model is wrong, your math is wrong, right? Or it could be the model that it could be a sign that your math is right, meaning that it does capture something that's supposed to happen in real life. Which is which? Well, again, right, you have to think financially when you do these things. It makes complete sense, right? For example, just think of what happens, right, around this point. What does that mean? For Tx close to TL, what does that mean? Right, I mean, not only that, right, you are very close to expiration, right? So basically, it's like one of those options that is, 1 day apart, 1 day to expire, right? But then you're also very close to being out of the money, right? Being striked out, right? So here, right, notice the option price is very sensitive, right? If you move like this, then you will get paid a lot, right? It's almost like the max pay you can get. But if you move in the wrong way, then you drop to 0. Okay, so the delta of the option here, I would say, would be huge. Or I don't know if it's the delta. Is it going to be a delta? Yeah, I think the delta. Or the delta is undefined or something, or the gamma is huge, whatever, right? But basically, it's going to be very, very, very wild right here, right? You have a chance to make a lot of money, or you have also a chance to just completely lose out your option, right? So this drastic, right, change in the option price, right, with similar move in the stock means that it cannot be too good, right? That means that one of the Greeks is really huge. I think it's a gamma, right? The gamma is very, very huge, and the delta is undefined. But right, you think about it, right? Here is where you don't want to be. The options behaving very, 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 very wildly, right? So that completely makes sense, right? Financially, that's very, very unclear where you're going. Okay. So yeah, when you are in this situation, that cannot be good. The second one, though, right, is now let's address Fatima's kind of remark. So maybe let me ask this, right? So if you stay within, right, the suppose I don't touch the boundary, right? Meaning I'm inside. What can you say about this? I mean, in terms of value, can it be 0? VTX. The value of the PDE solution inside the interior. What value can it have? Can it be 0? Yeah, it will always be positive. All right. I mean, this kind of comes from you understanding the PDE itself, the numerical PDE a little bit. But if you propagate back, right, because this guy is always positive, you propagate back. You know, you solve it, back solve like this is 0. You will always be positive, right? It will not be 0. Now, on the other hand, right, for a up and out call option, can this be 0? For an up and out call option, can this be 0? Right?
Yes.
So that's kind of what a Fatima is referring to, right? So what's going on here? Then the theory is nonsense, right? You solve the PD is always positive, right? And the option can be 0, right? You cannot claim that, you know, they match. What's going on? All right. So what's going on, right, is again, it's very subtle, but you got to read the description and the claim, right? The claim is this, okay? In other words, the claim is they only match when the option did not expire yet. Oh, sorry, the option is not striked out yet. Okay. So in other words, right, to answer Fatima's question, for this part, yes, you are right. That time is always in the background. But that background, unfortunately, cannot be captured by the PD. In other words, this PD is a PD for the option value Y not striked out yet. So in other words, when we solve for this, these are always understood to be values when you have not been striked out. But the PD itself cannot contain that kind of information. That information is not encoded into the PD, right? So any point where you solved here, you have to remember that this is the value of the option when it has not been striked out in the past. But that kind of information is not encoded in the PD. That kind of information has to be read from the outside. You understand? So that's why, right? And that is the limitation of the PD, if you will. I don't want to say it's a limitation. It's just about you need to know what the PD is trying to tell you, right? The object of the PD may not be directly the option value, but it's almost there, right? So the reason is, again, right, VT, when it has not been striked out, is the option value, or it is the PD solution. Otherwise, it's 0. Okay, so this piece is not encoded in the PD itself. That's it. Right, but if you don't pay attention and you solve for this and you think this is it, then sometimes it has been striked out and you report a wrong value. Okay. Any question? Okay. So now that would finish, right? Not finish what I want to say about P for up and out call. All right. Now we move on to the analytical formula for the call option for the exotic option in general. But before that, right, let me say this, right? We did not discuss down and in, right? Call up and out, up and in put, down and out, put, right? And these are all reasonable options, right? You think about it, okay? The logic may not be exactly the same as what we discussed so far because these options are slightly different, right, than what we discussed, especially the whole in part, right? What does it mean to be in, right, rather than out, right? I mean, the in part is very different from out, right? I guess the down and out probably is the closest, right, to the up and out. So you think about it, okay? When I say you think about it, well, you know, they may show up on your exams or that kind of thing, because that's when I can test whether you have been contemplating these kind of questions, right? So play around with that in your spare time. Okay, now let's talk about the analytical solution. So it so happened that we also, you know, will have the look back option also. Okay. So the reason is this, right? When you look at the pricing formula for either vary options and look back options, what you notice is that V big T in general is a function of the max. I mean, for that matter, it could be the min actually. So maybe when I say vary here, let me just say up and out, right? Because I mean, if you have something like down and in, down and out, and those are about the min. So you have to change a little bit. But you know, let me just, you know, be lazy, right? And just focus on the max, right? Look back, right, is clearly about the max, right? So in general, it's about a phi of the max. So suppose, right, let's forget the conditional expectation for now. Let's just look at expectation. So when you look at value at time 0, right, that would be this. Okay. Now, which, right, if you unfold it, is like this. Oh, sorry. Somehow I dropped the phi, right? Okay, like that, right? So that would be this. Now, one thing, right, that you I think you should get comfortable with is the max, right, and the exponential. I can move the max inside here. Oh, you know what? I apologize, right? This is small t, not big T. Okay. Okay, so far. Now, how can I move the max from here to here? Like this? What allows me to do that? First of all, I use that. Second, I use if what? Notice, right? For example, some of these things, right, we do very casually, but if you're from the math side, you know that these things are not always true, right? You got to have conditions. For example, what can make this go wrong? What can make the first relation go wrong? Right, right. If C is negative, then this completely is wrong, right? You'll have to change to a min, right? For example, and maybe a negative somewhere. I don't know, right? So similarly, right? Do we need any condition to change the max inside the G function like this? No, unfortunately not. That's not about that. What about derivative? Derivative of what? But derivative of what? G or F? Right. So you're thinking that, which is almost there, is weaker. If G is exactly, yeah, correct. Okay. Now, so notice, right? I have both of them here. That's why I moved it here, right? So now, let's say that, right? This plus is very tempting. So I want to maybe do a max of this plus the max of this, right? So while I'm right on the run, does that work? If that works, what condition do we have? Right? You understand why, right? I want to next. The whole point is eventually I want to isolate the Brownian motion out and take the max. Okay. But does that work? Or what condition does it work? Both are increasing function. Huh. Both are increasing functions. Not sure about that. I haven't really thought out what this is, but I just want to tell you this. This is not true in general. And it's unclear. I'm not sure there's a condition. right? What Jingmei was saying, I doubt. I have a vague feeling that it won't work. But anyway, right? Even if that's true, it won't work for prime motion because prime motion is not increasing, right? But here's the thing, right? Something like this cannot work in general. All right. Here's an example to show you. So for example, right, for F, suppose you have something like this, right? So this is F. And here's G. Right? Suppose this is 1, right? Then max F is 1, right? Max G is also 1. And max F plus G is
1.
Yeah, right. So clearly they're not equal, right? It's not max F plus G is not F max F plus G, right? So I wonder if so, right? I think we can change this to make a counter example to Jingmei's suggestion, right? Because I can do this. I'm not sure though. Maybe I'm not. Maybe not. I'm not sure. So if we do this, right? So max F is 1, max G is 1. What's max F plus G? Is it 2 now?
Yeah, 2.
Okay, so what Jingmei say may work. I don't know, right? So who knows? Could be. But so that could be true. Actually, let me think of that. Maybe what Jingmei says is true. But anyway, right? Even if that's true, right? That doesn't apply to right the ground motion because ground motion is not increasing, right? So yeah. Okay. Anyway, right? Let me try to see that. I have reason to just suspect that what Jing may say doesn't work either, but I have to come up with a counter example. Anyway, that's interesting. The point being though, right? Here we kind of stop, right? We cannot do more. But let me tell you, right? So what will happen is that at this stage, we'll have to do one thing further, which is a change of measure, right? We'll have to do a further change of measure. Right? So you define something like a W hat, all right, which is R minus 1/2 sigma squared T plus sigma W tilde T. Oh no, it's not true. You factor out a sigma because then you will make this into, yes. You factor out a sigma like that, okay? So now, basically, then this will be a Brownian motion. So you define, right? Define further change of measure so that this is a Brownian motion. All right. So on and so forth, we'll get there, right? And we don't really need to bother with this so much. But what I want to say is, all in all, you see that suppose that somehow, right, you can wave your hand and think of this as a Brownian motion under some E hat. The point is, the distribution of the running max of the Brownian motion is needed for analytical formula. Okay. And by the running max, right, I mean this guy, which you have seen before. Sorry, up to T, right? So in other words, we want to be able to calculate this kind of thing. And, you know, other kind of expression, maybe, right? So you understand why, right? Basically, because in an option pricing, right, this, if you collapse it to another Brownian motion, when you change measure, then essentially you are looking at the distribution of that max. Okay. So to understand this, right, to understand the distribution of running max, unfortunately, you see it's not an easy object to get. We need something called a reflection principle, which we'll discuss next week. But also, you see, we're getting very close to that, the formula for the H function. Right? So that gives the whole explanation of why we have that function, right? That basically we'll have to deal with the distribution of the running max. It will turn out that we have to get a joint distribution of the running max with the Brownian motion itself. And then from there, right, well, once we derive that and we derive something like an H function, then we can use the H function to describe the price of the you know, of a Berry option or a loopback option. All right, so that's the story. Okay, so this is we will stop here and then we'll pick up. All right, next Monday.
Thank you, Professor.
Yep, thanks. Thanks.